broad overview of black hole microstate counting in string theory, um, which is my main research focus. So, as you know, string theory is a candidate theory of quantum gravity and perhaps, hopefully, much more. And black holes are more real life objects, and my research area is in their intersection. Before I go into detail, I just want to stress that this is somewhat of it's a very interconnected topic. In particular, it takes a very central place in string theory. So lots of very curious features of string theory like duality, supersymmetry, extra dimensions, solitonic objects, all these things come together in this black hole thing. The most relevant and popular outgrowth of string theory, that is holography, this also came out of black hole physics. In recent years, people have made connections with like very non-stringy things like phases in quantum matter without quasi-particles, quantum chaos, or semi-classical chaos. It connects to various branches of mathematics as well, like quiver representations. Black hole degeneracies very often have modular structures. There are connections to numbers theory and so on. Okay, so the big picture is the following, which you all know, of course, is that as of now, our understanding of fundamental physics relies on two pillars: quantum field theory and general relativity. The first one describes all the matter and three forces, and the fourth one describes gravity. Now, by the simple fact that in nature they coexist, it must be that their theoretical principles behind them, they must be consistent with each other. We should be able to reconcile them. Now, our sort of instinctive attempt would be then to quantize gravity as a field theory. That doesn't work out due to denormalization problems. Perhaps that's not too unexpected, because GR is a very different kind of field theory. In all other field theories, you have the stage set, that is the space-time, and then you have drama happening on that stage. But in GR, the stage itself is the drama, which is very different. Then you can take a step back, and the next best thing you can hope for is that, can we take at least classical gravity, a GR background, and do QFT in that background? Is that consistent? It might seem hopeful because flat space-time is a GR background, and we know QFT works pretty well there. But as soon as you move to black hole backgrounds, you get rather confusing things. So even that doesn't completely work out. And black hole comes into the story because, the story started because of this, that people studied QFT in black hole backgrounds and found funny things. And so to sum up, it turns out that to understand quantum black holes, you need to understand quantum gravity, which in particular means that there should exist a theory of quantum gravity. And of course, in understanding quantum gravity, quantum black holes play a very central role. This is the big picture, and string theory being a candidate theory of quantum gravity, we'll see how string theory, how it does. Okay, so this is the broad picture. The talk would be divided in these segments. First, I'll give a somewhat more elaborate introduction of the relation between black holes and quantum gravity. This is all well-known fact. Then I'll go on to give the broad idea of the logical structure of black hole microstate counting in string theory, and then I'll come to explicit examples from my work with some hints of future works. Okay, and do stop me if you have any questions. I should have told that before. Okay, so before we talk about classical quantum black holes, we must talk about classical black holes. Now, their claim to fame, of course, is that nothing escapes a black hole. Nothing includes thermal radiation, and in our traditional understanding of temperature, if an object has temperature, it emits thermal radiation. Therefore, if something does not emit any radiation, it should have temperature 0. from a more theoretical perspective, that is thinking of black holes as solutions to Einstein gravity, you also expect that they should not have any entropy, simply because black hole solution, be it Schwarzschild, be it Kerr, be it Reisner, Nordstrom, all these solutions are entirely fixed by a few charges. So once you fix the charges, there is not much room to put structure in. So you do not expect classical black holes to have entropy. Now that is not a very nice thing, simply because think of our sun. I don't know whether it will collapse to form a black hole or not, but some star which exceeds Chandrasekhar limit will collapse to form a black hole. Now the star has a lot of information, a lot of entropy, but once it collapses to form a black hole, this suggests that it should lose all that entropy, which clearly is in tension with second law of thermodynamics. Things are not very well. Now, in an independent line of development, people like Bardeen, Carter, and Hawking, they were studying problems like if you have two black holes and then they collide to form a new one, what are the laws that govern such processes? And they found that the laws, which they called laws of black hole mechanics, they have remarkable resemblance with the laws of thermodynamics. At that point, it was not entirely clear whether it was just a fluke or there is something deep about it. Then came Hawking, and he considered this problem, that you take a Schwarzschild black hole and you take a scalar field, you consider a quantum field theory. You start with the vacuum state in past null infinity, and you ask, what do I see at future null infinity? And he found that an observer at future null infinity observes thermal radiation. So this was interpreted as the black hole radiating thermally, because the field was in vacuum state to start with. In particular, this confirmed that this was more than a fluke. Black hole does have actual temperature, and it resonated well with those formulae. And in particular, it fixed a precise formula for black hole entropy, which is a quarter of the area of the event horizon in Planck units. Okay, that's very nice. This tells you that black holes are just another thermal object, but not quite just another, because entropy is typically an extensive quantity. It goes with volume, but here it goes with area. I mean, this observation is the root of holography. But now we have a new puzzle, which is, where does this entropy come from? Now, in classical physics, it's not only that we cannot count the microstates, but we do not have any clue whatsoever what the microstates could have been. But the appearance of Planck length, this gives you a very strong hint. Planck length is the characteristic length scale of quantum gravity, because you have quantum, you have gravity, you have relativity, all that. So this formula tells you that somehow the answer should lie in a theory of quantum gravity. This is why quantum gravity is important for quantum black holes. It's also true the other way around. So if you have the characteristic length scale, the characteristic length scale of quantum gravity is Planck length, and the corresponding energy is extremely high, much higher than, say, the LHC energy. So whatever theory of quantum gravity you come up with, string theory or not, it would be extremely difficult to test it, at least in near future. So in the meantime, we can stop thinking about quantum gravity. That's one option. Another option is that we can look for very stringent theoretical tests and check whether our theory passes those tests. And black hole entropy provides us with such a very stringent test. You have a formula. You should be able to, first challenge is to come up with the microstates at all. That itself is challenging. And then you have to count them to reproduce this exact formula with the factor of 1/4 and all that. So of course, very stringent test. So this is why we are interested in quantum black holes as string theorists. As I stressed, it so turns out that all these funny features of string theory, they sort of come together in making this work. So once it works, it kind of validates the not so obvious structure of string theory. Okay, now I'll quickly tell you about how the broad structure of microstate counting in string theory. Before that, I just want to give a quick intro to why string theory is a theory of quantum gravity. It's somewhat intuitive, but any question before that? So string theory, as the name suggests, is a theory of strings. Now think of a closed string. In space-time, it will carve out a cylinder, and we typically do string theory in a first quantized formalism, that is to consider the space-time coordinates as fields in the string worldsheet, and then we quantize that field theory in the string worldsheet, and the excitation spectrum, that is the spectrum of states in string theory. Let's forget about interactions for now. Now, since there is one direction, there could be, an excitation could be either left moving or right moving, right? So we'll expand the fields in left moving and right moving coordinates. In the free theory, they are independent. So independently, you quantize the left moving and the right moving part. There are some constants, but it's okay. Then, as you can guess, that each field will, space-time coordinate will give rise to its own creation of operators, its own spectrum, and in the full theory, you will take a direct product of this left moving sector and the right moving sector. Without doing the detail, it's pretty obvious that you will have oscillators carrying this index mu both in left side and in right side. Then you will in particular have states which will have this structure, not all states, but some of the low lying states, that one index coming from the left moving sector, another index coming from the right moving sector, which of course is the rank 2 tensor, and in particular it will have irreducible part, which is the symmetric traceless part. This we can identify with gravitons. So this is really a bosonic string theory picture, which is not even a consistent string theory, but it makes the point. This is how it roughly works out. Okay. The remarkable thing here is that this string theory is UV complete. That is the challenging part. And from a UV complete construction, you are getting a graviton. That part actually is quite effortless. The challenging part is that you get a lot more and making sense of that lot more. Anyway, but that's not our concern for this talk. Okay. These are also well-known facts, but I thought I'll just remind. So string theory, of course, tells that fundamental entities of the universe are not particle-like, but string-like. You can rephrase this as saying that there are infinitely many particles corresponding to various oscillation modes of the string. It also tells that nature is supersymmetric, never mind what you find in LHC. It tells that the number of space-time dimension is 10 as opposed to 4. And it also tells that the story doesn't stop at strings, there are membrane-like objects as well. None of this seems to make sense with what we already know about the world, but it might. For example, the typical energy scale associated with a string would be inversely proportional to its length scale, and if the string is very tiny, that scale would be very high. Now, you will see the stringy structure once you do experiments in that scale. Below that scale, it will look like point-like. So it might still be that why it seems to us that the fundamental entities are point-like. Then supersymmetry. It might always be that it's broken at some high enough energy scale. For us, high would be high compared to what we have found. And then comes special 6 extra dimensions. Again, if these dimensions are small, the corresponding energy scales will be high, and we will need very high energy to see them. And regarding membrane-like objects, well, the point is that they are allowed by the theoretical structure does not mean that the particular vacuum we live in, they have to be there. So it's possible to make sense of this bizarre thing. Okay, now we come to black hole microstate counting. Before I go in detail, I just wanted to give a cartoon of this. The basic idea is, I think, quite intuitive. So the space-time as per string theory is somewhat like a cylinder in the sense that it has its product of a non-compact part where we live, and then a compact part which we do not see. Uh, but yeah. Now, so to us, space-time looks like this non-compact part, just R31. Now, if you have a point-like object in this R31, uh, one, so the question is that if you see a point-like object here, what it might be in the full string theory. Well, forget string theory, just think about geometry. In the full geometry, it might be that it's still a point-like object, but it can also be that it is an, say, it's like a rubber band, an extended object, but extended along these compact directions. So we do not see the extension from this side, from the in low energy in R31. What's the big deal? The big deal is that if you have a truly point-like object, you do not expect it to have too much structure. Might have spin and so on a little bit, but not too much. But if you have an extended object, it's conceivable that it can have much structure. So the big deal is that here it looks point-like, but if the full story is this, it might be that although the nature of the microstates are not clear here, but there is, but you still see the microstates in some sense because they are there after all. This is basically how it works out. This point-like object here would be black hole for us, and this rubber band would be the corresponding system of d-branes in the full string theory. This circle would of course be a 6-dimensional space, generically a Calabi-Yau threefold, but the simplest case, which will be relevant for most of the talk, is just 6 torus, a product of 6 circles. Do note that extra dimensions are crucial in this story. Now a bit more detail. Any question till now? Okay, now I'll get more concrete. So the starting point, of course, is string theory in full 10 dimensions. Then we say that, well, I do not care about the full string theory, I care only about the low energy modes. So we restrict to the massless field content of string theory, which is described by 10-dimensional supergravity theory. So we come to a supergravity theory. Good. Then we say that, well, but we live in 4 dimensions, so we do not care about 10 dimensions. Then we dimensionally reduce to over these 6 dimensions to get to a 4-dimensional supergravity theory. Depending on the choice of the 6 manifold here, this theory can have different amounts of supersymmetry and therefore different field contents and so on. But you have a supergravity theory, that's the point. And being a gravity theory, it has black hole solutions. These black holes have Bekenstein-Hawking entropy. So we have got the entropy starting from string theory in this manner. Okay, of course this doesn't tell us much about the resolution of the puzzle. The point is there is another way of thinking about the same black holes in string theory. And that way makes it possible to count the microstates. Okay, let's again start with the black holes. Actually, let's start here in the supergravity. Being a supergravity theory, the fields will come in supermultiplets, and since gravity is in a spin 2 multiplet, you will also have spin 1s, that is, you will have a lot of U1 gauge fields. So there will be objects in your theory which are charged, possibly electrically, possibly magnetically, or perhaps both, under those U1 fields. So as you would expect, there are black hole solutions which are both electrically and magnetically charged under various U1s here. Okay, we will restrict to those black holes. Now we note the following, that this supergravity theory was obtained from dimensional reduction of a 10-dimensional supergravity theory. So the gauge fields here, they also came from something here. They are typically fields carrying, like gauge fields are one-form fields. Here you can have more, higher rank tensors, and if one of the legs are along this 4th dimension, but remaining legs are along the 6 directions, from the low energy theory, it will look like a one-form field. In particular, you can have higher form fields here, and you do have higher form fields here, which after dimensional reduction will lead to one form fields, the gauge fields. Once you note that, the obvious question is that what are the charge carriers of these higher form fields in the 10-dimensional theory? And they turn out to be membrane-like objects. People used to call them p-branes. The next question then is that, is there a way of thinking about these p-branes more fundamentally in the full string theory, not the supergravity, not the 10-dimensional supergravity. To my knowledge, it took quite a few years to appreciate that, but ultimately it turned out, I mean, Polchinski figured this out, that these memory-like objects have a rather simple description in the full string theory. They're like walls where an open string can end and get one of the ends of the open string can get attached. They call D branes. D stands for Dirichlet. So open strings have Dirichlet boundary conditions along that direction. They can't move. Okay, so to summarize, the U1 gauge fields under which the black hole is charged, in the full string theory, those same charges are carried by D branes. But the beautiful thing is that you have a more fundamental description of these objects in string theory. They are inherently quantum mechanical objects. So, what looks like a black hole carrying a bunch of charges would actually be a system of like a bound state of certain D branes. And there you can usually write down a low energy theory with some effort. The microstates are quite apparent, you can count them, and then comes the fateful moment that does this counting produce this entropy or not. If it does not, it's a death blow to string theory, because it tells you that there is something wrong. But of course it does. In all the cases where we could do it. Do note that here you do not necessarily get log of an integer, but here the microscopic counting gives you a precise integer. Okay. Now I'll get to more specifics related to my work. I'll give concrete examples. Any question till now?
Yes. So it seems what you're describing really is kind of micro black holes. Is that right? So does that also explain then the entropy of larger black holes?
So, okay. I will actually revisit this in, related to an work of mine. So the point is that these descriptions are valid in a somewhat different regimes. When we talk about black holes, we are of course assuming that GR is a good description, the black hole is large enough. In this description, okay, so the charge of the black hole translates to the number of D branes, and this description is valid for any number of D branes, small and large, but gravity is ignored here. Newton's constant is very small. So when you say large black holes, it's true that this picture is the Bekenstein-Hawking entropy story is for large black holes, but the largeness here is really embedded in Newton's constant, not in the charges so much. But yes, it's true that the match is really expected for large charges.
Can I ask, I know now of several models, the black microstates anyway cannot be seen. So what is important is the entropy formula, I suppose. Now I know of 3-4 theories which all produce the same formula. Which, for example, original Raffles-Orkin paper, recent DCTS paper by Bitton, Longo and so forth, using Tomita Takesaki theory. Then there was some other paper, loop quadrigravity. All of them give the same answer. So why should one defend this model?
Well, they should defend their models, I'll defend mine.
There are 4 models. It is not like investing in some stock market. Here with the...
Well, I do not have any, I mean, I cannot prove that this is the only consistent theory of quantum gravity, and I'm not claiming that. I'm saying that this seems to be a consistent one.
But also there is a theorem, research I think by David Gross and somebody else, that when you sum up all the terms for the string theory, it diverges.
In which computation?
In PRL. There is an ultraviolet divergence.
All terms
in string theory.
I mean, in a scattering amplitude computation, in which computation?
I am not a string theorist, but I believe that it was a, this I don't remember, okay? But there was a paper in PRL by David Gross and one of his colleagues, okay, where they tried to add up, like Kazakov formula or something, okay? They added up all the terms, tried to estimate, and they found that there was divergence, incurable divergence which cannot be Borisov.
So
Definitely. I don't know whether it's correct or not, but
I mean, divergence in what? I don't know about this. I have to first.
As far as I know, the area law, I mean, under string theory, only one loop commutation has been done, like when you are taking for the black hole part. And that is just one loop and that does not carry a divergence. But,
no.
the,
This is a
but that
summation
is
of
all
all.
that is known.
This is an infinite sum.
But then it probably is not in the black hole picture. Because black hole picture, as far as I know, it's only one loop has been done.
In the microscopic picture, you get the full answer. You get a precise integer.
It should be comprehensive, no? It cannot be bit here and bit there and bit somewhere else. There should be some overall picture. And maybe it's irrelevant, I don't know. But I know of this paper.
I think that was a string derivation theory, well, it was summing up world diagrams. Was this not summing up string world diagrams? It was
Just a summation of
string theory
diagrams.
definition.
It's very much like infrared divergence in quantum field theory.
Oh, infrared.
No. It is that calculation I remember, again I may be mistaken. But this kind of calculation has been done in QED by Bloch and Nordseek and many other people, and Kibble. So, in the calculations of Kibble it was infrared. Okay? But from what I remember, it may be wrong, David Ross's paper is not infrared.
I'm very surprised it was UV divergence.
I don't know whether it's constructive to debate something none of us know anything about.
Except maybe in the coffee breaks.
No, maybe I'll have to see that paper.
Yeah, I think we should continue because and
Okay.
check it out later.
Yeah, but as you will see, we will have precise integers.
But anyway, there are many models which give the same answer. At least as far as we can check experimentally. Or check with black hole entropy. So which one do I pick?
We should do finer tests, I think.
I think that's a good question, but he at least is putting this one into the pool and he's trying to say does it pass this test?
But it was presented as an ultimate theory.
No,
At
that's-
least
I did not say that.
propaganda.
I did not say
He didn't
that.
do that, no, in fairness he did.
Okay. Okay.
Yeah, this is. Yeah, so here's one concrete example. You'll get a feel of how things work. So there are, of course, many supergravity theories. There are many kinds of black holes in those theories, and correspondingly many different microscopic descriptions. Sometimes for the same black hole, you can have equivalent, different microscopic descriptions, but related by dualities. So this is not a very representative of everything that is there. It's just one particular microscopic description. Okay. So let us consider the simplest supergravity theory, which has the maximal supersymmetry n equals to 8 supergravity in 4 dimensions. And we'll talk about black holes that preserve 1/8 of this supersymmetry. Okay. This supergravity is obtained by dimensionally reducing over the simplest choice of the 6 manifold, the T6. Okay. We'll further choose the charges such that the corresponding ion fields, they come from higher form planes whose charges are carried by these d branes. The microscopic description of this particular black hole is given by this system. So you have 4 stacks of d branes, one stack of 2-dimensional membranes which we call d2 branes along say 4 and 5 directions, so it's a 2 torus. Another 2 torus along 6-7 direction, another 2 torus along 8-9 direction, and then a d6 brane, a 6-dimensional membrane along the entire 6 torus. So the flat spacetime is 0, 1, 2, 3, and these are the rest. Okay. Note that this d-brane system intersects at a point. So the low energy theory would be a 0 plus 1 dimensional theory. This is not the most popular case. Typically, in microstate counting and string theory, people typically come up with descriptions that are 1 plus 1 with CFT. This is not like that. It's a bit different.
So what is the graph?
Yeah, I'll talk about it. So the goal, of course, is to come up with the low energy theory. For that, we need to first identify the low energy degrees of freedom. the low energy excitations of a D brane, they are given by open string stretched between the D branes. So if you choose any pair of D branes, the picture is somewhat like this. You have two D branes intersecting like this. Of course, this line represents two torus. This line represents another two torus.
So you are putting the metric in.
Flat.
Hmm?
Flat metric.
So it is not, it is a semi-classical calculation. Because how do you say it is intersecting transversely without a metric?
He has a metric in there.
It's yeah.
It is not quantum gravity, it is some semi-classical gravity.
Well, these things are done okay. These things are done around some background, and that background I choose to be Minkowski one in the sixth direction. The quantum thing is that the excitations will include a gravitron. Yeah.
That is not a, okay, we talk later.
Yeah, this criticism exists, but okay, something is better than nothing. Anyway, gravity will not be important for this particular task. Okay. There are two different kinds of open strings here. One kind of open string which start and end on the same brane. Another kind of open strings that start and end on different branes. These open strings, they give rise to matrix-like fields. So, like each end, so the thumb rule is that each end corresponds to like one index. So we have two indices here. Here also you have two indices, but we choose to take these D2 branes to be only one in every stack, whereas we choose the D6 brane to have, I mean, we can have n D branes, n D6 branes. It's a choice. You could have taken some, let's say, n1 D2 branes here, n2 D2 branes here, n3 D2 branes here. But it turns out that for this purpose, this simplest choice works, it suffices. So therefore these strings, when they are stretched between the D6 and another brane, then these give rise to vector-like fields, and these give rise to matrix-like fields. Okay, how do we see the supersymmetry? The thumb rule is that, yeah.
Just one thing, like the two D branes that you have drawn, they are D2 branes. Like
Might be D6 as well.
it,
So
like
starting.
it can be like D6 or D2.
Both, yeah,
Both.
can be. Yeah, let's just quickly see the supersymmetry. So the black hole preserves one in. How do we see it in the D brane picture? The thumb rule is that each D brane breaks half of the supersymmetry. So the first preserves n equals to 4. Then when you add the second, it preserves n equals to 1. The third, n equals to 2. Then you add the third, it preserves n equals to 1. It so turns out that if you add the last one with correct orientation, so you can have D branes and anti-D branes. You have to make the correct choice. If you do that, then it does not break any further supersymmetry. So the whole system preserves 1/8 of the supersymmetry in 4-dimensional language n equals to 1. This in particular implies that in the low energy theory you should be able to arrange the multiplex in n equals to 1 super multiplex. We do that, then we dimensionally reduce to 0 plus 1D. With some physical intuition and some inputs from supersymmetry, we are able to write the Lagrangian to significant extent. And then what do we do with it? Wait.
So again, about
Sir.
the space-time here is 1 plus 3 dimensional, is that right? And you said 0, 1, 2, 3 are space-time dimensions.
Yeah, so for R1.
So where is the 0 plus 1 dimensional theory living?
So
Is that in
One is
space-time?
this one time.
Oh, so it's 0 space and 1 time.
Yeah.
Oh, okay. Okay, so it's a line.
Yeah.
It's a line in the positive. Okay.
It's just quantum
It's
mechanics.
one line.
Any other question? Yeah, so what do we compute? So we started out to reproduce the entropy, so we must compute the degeneracy. Here is a bit of technicality. So this being a supersymmetric quantum mechanics, there are two kinds of states, bosonic and fermionic. And the degeneracy we are looking after is a sum of bosonic ground states and fermionic ground states. Now, for a supersymmetric black hole in 4D, which is spherically symmetric, it's a case we are looking at, you can argue that all the microstates carry, I mean, for all the microstates, the I mean, they are boson, the number of fermionic states is 0. This trivially implies that the sum of the bosonic and fermionic states is same as their difference, but the point here is that their difference, which is known as the index, this guy does not change under smooth deformation of the supersymmetry quantum mechanics. This is important because, as I was responding to a question, the big difference between the black hole side and the de Broglie side is we have changed the Newton's constant a lot. It's significant in the black hole part and it's insignificant in the de Broglie side of the story. So what should not change is the index. But since the index was same as degeneracy to start with, it suffices to compute the index in the de Broglie picture.
Just so I can understand the model in the end. So it's a matrix model. So you have some joint matrices. So you have matrices for some fields. I'm not quite sure how many matrices. How many you have.
Okay, I should maybe detail a bit more. So it's
You also have vectors, presumably. You have spinors that are matrices.
yeah.
You have joint ones coming from gauge fields. You have vector.
I have vector. I also have scalar.
You have vector representation, so they're not matrices, they're just vectors.
Yeah, from these strings. So on each de Broglie you have n equals to 4 super elements. You reduce it to 0 plus 1 dimension.
So n equals 4 is going to be a BFSS model. And you reduce it.
True.
Okay.
But different fields will appear in a bit different footing due to intersections and so on. So you have 4 copies of n equals to 4 super elements. One of them is non-abelian.
And then you have some vector representations, or 1 by n matrices from your.
Yes.
And you have how many of those?
Yeah. So for each pair of de Broglies, these will come in n equals to 2 hypermultiplets. So n equals to 2 hypermultiplets, which has 2 n equals to 1 chiral.
Yes.
So you'll have complex scalars corresponding to each pair of de Broglies.
Yes, yes. Anybody each of the BFSS has the same n. They're the same size matrix.
No, no.
They didn't have to be, but.
No, no. Just one of the BFSS has n, rest of the 3 are abelian.
Oh, you see, there's the tree over here. Okay.
Yeah.
All right.
I have two questions. So one is like, do you have a simple understanding why this omega f, like the number of fermion zero modes should be 0?
Yeah, it's a symmetric argument. So you look at the near horizon AGS2 symmetry, the SL2R, and you have supersymmetry. You see that the algebra closes up to an SO3. So if SL2R is a genuine symmetry, which you know is the case for extremal black holes, and if supersymmetry is a genuine symmetry, then it must be that all the microstates carry vanishing charge under SO3 also. This means that they carry zero angular momentum, which of course means that they are bosons and therefore not fermions.
But like generally when you break the supersymmetry, there are like some
Goldsteinos?
Goldsteinos, so that actually becomes like that is necessary to count in n equals 4 supersymmetry theory.
Yeah, so what we really count is, it's called, in this case is 14th helicity supertrace. The end effect is to throw out the Goldstone multiplets. So you can forget about them.
And another question was like you were saying that this G Newton you are increasing and decreasing in the two pictures. Like can you show what equation or how do you do that?
It's more intuitive than precise equation.
No, but then what does it mean that G Newton in 10 dimension? What are you meaning with that? Or like you said that in the de Broglie picture G Newton has a less value than the other one in the 4D.
I mean, I am doing the computation. In my computations, I'll ignore gravity, and I'll justify that by saying I'm working in a regime where G Newton is very small, which you can do in string theory because it's a wave, it's related to some waves. It's not an external parameter.
So you can increase or decrease G Newton's value
Yeah, by tuning the waves. Okay, I'm doing bad with time, I think. Uh, should I move on? Should I continue?
Yes, I think you
Question.
can, yeah.
Okay.
I missed the last sentence you said.
No, we were just talking. Haradit asked some questions. And, yeah. Anyway, so the final task is then to compute the Witten index. Sorry, an name is missing here. The Witten index in the supersymmetric quantum mechanics. Now, we further know that this index is same as the Euler characteristic of the vacuum manifold. That is the manifold in which the potential vanishes. The potential in a supersymmetric theory is typically a sum of squares. You have these f terms and d terms. So the vacuum manifold is simply the solution space of the corresponding equation. Just set those d terms and f terms to 0. So it's a pretty algebraic description. So the first task, of course, is to figure out the solution space, and second task is to compute the Euler characteristic. Just to give you a feel of the equations, you do not need to see the detail, it's not important. All I mean to say that these are polynomial equations, and you have at most cubic terms here. These phi's are matrix-like fields, z's are vector-like fields. The rest are not important. There's a gauging variance story, but okay, never mind. Then a simplification happens here in this particular case, that the vacuum manifold turns out to be a set of points. So the potential is somewhat like this. There are some discrete minima here and there, and then the task is to count the minima. That is same as counting the number of solutions of that set of equations. Now, this counting was already done in a different duality frame by Strominger and someone else. Anyway, so the microscopic degeneracies were known. This gives you another way of reproducing them, or rather checking the duality. So what we did is that we put this system of equations in Mathematica, which solves them and therefore counts them. We could do it only for small charges because the system gets very large, intractable. And
N is the number of DC units.
exactly. So for low charges it's like this, but as I told you, we get precise integers. I mean, it's not that you'll get some correction to it. It's 12. It's not 12.5 or anything. And just to give you a feel for the match with the black hole entropy, actually one look at the corrected one. If you take the log of the first line, these are pretty small charges. You really do not expect a very good match here. These are, I mean, black hole is not a very good thing to talk about for such small charges. But still, you get a pretty good match.
What is the asymptotic number you're aiming for?
Oh, so the first line is the microscopic computation, and this is the vacancy knocking entropy on the character. And this is the log of the first line. So I expect the second and third line to match for all n's. And the match gets better as you increase the charge. That's the point I'm trying to make.
But n is supposed to be fine.
N is finite. By finite you mean not very small.
Presumably, the match is perfect as n goes to infinity, is that the idea?
Yeah.
So n is the size of the joint A.
Yeah, in this language, yes.
Of your file.
So the charge of the black hole is like the black hole you're talking about carries 4 kinds of charges. 3 of the charges are 1 and 1 charge is n.
So just the black hole formula that you're matching with is
Oh, I did not.
It's area over 4 times L Planck square, but how do I compare?
I am actually comparing with one loop corrected entropy. For that computation is also done in string theory. I have not shown that expression.
You didn't show us how you're going to concretely compare because the area is not obvious here.
It's not exactly.
So how did you get the number 12.409 to compare with, for instance?
Which one?
The last one, or the first, any of them. Just how did you get that number?
First one I got by taking log of this.
That's
This I
easy.
explained.
That's what we can see. The bottom line is the one that's invisible to us.
Oh, for this there is this mechanism of change entropy function computation. So you say, okay, for this side you set up the computation in the near horizon ADS2 and you do a path integral there and that reproduces a number, not integer.
You're asking for the scale. I mean,
I'm asking, I know that the formula is going to be the area over 4 times L Planck squared, and it isn't obvious to me what the area should be for a 10, n equals 10 matrix model for this black hole.
You mean the microscopic
That
side?
part is clear. The bottom line is not clear at all. How you make a comparison. You've got a number 12.49, but you've given us no hint as to how you compute its 12.49.
Oh, I took this as really inputs because other people had already computed.
But how did they compute it?
Is there some classical solution associated with n equals 10, which is a black hole and 3 plus 1?
So in the black hole side you have black hole solutions. What you do is that you take the near horizon limit, you get an ADS2 times S2 space. You can compute the entropy by computing an path integral there.
Yes, but that's going to give me an area and
The leading term is area, but then there are corrections.
but even if I did it, even if I forgot the corrections, I wouldn't know how to take the area over 4 Planck squared and get something close to 12. I would get, I'd say, well, what is my area? The area is, I don't know what it is.
Maybe I'm not understanding the question.
How do I translate the area over 4 times the L Planck squared into a number?
It is
Which-
a dimensionless quantity.
It is, but I don't know where n is appearing in it, and I don't know.
Oh, area depends on the mass depends on charge. Charge has n.
These are extremal.
Yeah, these are extremal black holes, so charge equals to mass.
The area depends on the mass, that's true.
And mass on charge because these are extremal.
So what formula are you using? I still don't know what formula you're using.
It's not.
Maybe some Brian was.
Well, I'm assuming there's a classical solution in here.
Yeah. There is.
But a classical solution won't help me unless I know how to put the inputs. I need to put the matrix 10. I can't put 9 in. I have to put 10 into it.
Is there a classical solution associated with different values of n?
Yeah.
Value of n
I mean,
is different
like
values.
Schwarzschild solution, mass is a parameter which you can change. Here also charge is a
Mass depends
parameter.
on n.
Yeah.
So the Schwarzschild radius depends on n. If you have that explicit.
And you have an explicit formula for
Yeah, it
that
exists.
one. And you're using the fact that L Planck also, G
Oh.
Newton also scales with n.
Not with n, I think, but yeah, this is important.
This is the part that's missing for us.
Uh,
Make any connection and all this. This is a crucial formula.
So one key point here is that G Newton in string theory is not an external parameter, unlike in GR. It is related to waves of various fields, and once you compute, you do the full computation in string theory, every dependence apart from numerical ones, they cancel out. It's not very obvious at all.
So area, you are saying that this is going to be a dimensionless quantity.
No. Area scale.
Area over 4 over L Planck squared is the matrix. So can you roughly put the n into that formula for us?
I can do it for n equals to 2 black holes, which I remember top of my head. For n equals to 8, I have to see. The thing is that there are too many fields and things are interacting. So
No, but
it's
still,
not like
roughly
right or
what
not
is
wrong.
roughly what is the cancel? How is
So
the
if you have
cancel
just
doing
one
that?
D brane, which is not the case, you do not have a black hole for a 1D brane. For a single D brane, it would be like n.
But it clearly doesn't scale with n, so there's a much weaker scaling with n because
Is that a large n? You say?
going
Is that a large n result? Is the mass proportional to n for large n? Is that?
that seems unlikely as well.
It's
Brian,
for a
because if I
single
look
D
here
brane.
at-
The bound state will change the story, and I don't remember the exact form.
If I go from 2 to 4 to 8, if I go in factors of 2, it's going up from 2 from almost 5 up to 8 to 10. So it's going much slower than a single power van.
My recollection is that it goes like it will be rooted, some number here.
Okay. And that's the crucial formula for us to follow.
Oh, that's what you were asking. Sorry, I seem to.
I sorry.
No,
Yeah, I
I
should be-
still have another question, like
Uh-huh.
how the LP square cancels in this expression?
Okay. I can only sketch it. First of all, it's not immediately obvious. So LP has what? G Newton, H bar, C. These are given parameters. You don't play with them. But this guy is related to wave of various fields. Now, once you compute the, these waves specify the background also. So when you compute A, the black hole solutions, these guys have a same. For example, okay, if time permits, I'll go to n equals to 2 example where it will be more explicit. Then you'll see the mass explicitly depends on these waves, and therefore you will imagine the area will depend as well. So it's conceivable the same entities appear here, and they might cancel out. It's not obvious. Not claiming it's obvious.
H bar was like 1 upper n, usually is the translation.
I don't think we are playing with H bar.
H1 and C are one.
Yeah, they are fixed.
Usually in these matrix models, H bar goes like 1 over n because you want to suppress a large n suppresses the quantum mechanics and you get a classical supergravity playing a role.
You mean 1 by n plays the role of an
Yeah. So
that
H bar is only not relevant if you go to the very large.
true.
Anyway, it would be nice to see what that formula is that compares them. That's all. We don't need to
I
do
think
it
I
now.
have the formula in my paper. I can check and tell you. Okay, I'll skip this. I'll skip. Okay, I think. Oh, I just have 1 minute suddenly.
No, you started late. Don't panic.
Okay, so how much time do I have?
You have at least 10 minutes.
At least 10 minutes. So I had some future plans on this work which I'll just simply skip, and I'll rather go to another recent work of mine which perhaps sheds some more light. Deals with a qualitative issue. Time permits, I'll come back to things I skipped. So this particular work deals with the playing with Newton. Okay. So the current situation is this. We have a black hole description which is trustable when, of course, the Schwarzschild radius is large. And we have the deep range description, but the way we do the computations, we ignore gravity. So we take Newton's constant to be very, very small, which we can do because it's not an external parameter in string theory. To put differently, this guy is large here, this guy is small here. Now the questions lie here, but we somehow give the answers here, which is not very desirable situation. Ideally, you would like to understand the microstates here, right? I mean, we would like to have some picture, perhaps 1 microstate per unit area, something like that. But you do not have such a picture. So, in best of the worlds, what we would like to have is a microscopic description here, which is easier said than done. More realistically, we might aim for starting here, where we do understand the system, and somehow turn on effects of gravity, switch on gravity, and perhaps have some microscopic description here. That will be some progress. This we achieved for half-deep black holes in n equals to 2 string theory in this recent work with Short. I'll give only a very broad overview. It's not very technical anyway. So in this particular case, the ignorance of gravity, it comes as follows. So there the okay. It's a bit detailed. I should have put some pictures. Anyway, okay. So when I'm writing down the deep range description, I'm making certain assumptions. Like, I'm thinking of D-branes as geometric objects, as you pointed out, and using classical geometry, and so on. Here, the D-brane description, which I have not told you what it is, that description is valid in a regime where the Taylor modulus is very large. Taylor modulus fixes the size of the Calabi-Yau threefold, so you have the Calabi-Yau threefold to be very large. This is exactly opposite to the situation in which you do dimensional reduction. So in this regime, Newton's constant is negligibly small. The low energy theory of the effective system, which I have not told you, that is captured by a two-dimensional conformal field theory. Maldacen, Strominger, and Witten figured it out. So it's called MSWCFT. Yeah. Now, I have not shown you the detail, but taking this scalar modulus to be very large, that amounts to taking the Newton's constant to be very small. I mean, there's an explicit formula relating these two. So, what we try to do in the system is that suppose we start here and then we take this scalar modulus to be finite. That would take me in a regime where gravity is no longer negligible, and we ask, can we construct a microscopic description of this system? And we believe we are able to do that. So the existing story in this case is the following. You have a four-dimensional black hole, then you intuitively do this and you get a very different picture. Another way of thinking about this is that you start with a given black hole, fix the charge, but now if you tune the Newton's constant to be very small, the black hole becomes small, and once it becomes very small, you need to take quantum effects into account, then it looks very different and turns into a bunch of D-branes. Another element in the story is an radius 3 space, but we'll not go there. Anyway, so the question we ask is that if we start here and go the opposite direction, what do we get? In this particular case, much about the microscopic theory can actually be seen from the black hole side. For example, this being a half dps state n equals to 2 theory, the mass is mod of the central charge as per standard supersymmetry algebra, and the central charge is this. So you see the modulus J appearing here explicitly. So this is one concrete example of how the mass depends on the charges. PQ and Q naught are charges carried by the black hole. P comes from a D4 brane, it's a magnetic charge. Q and Q0 are electric charges, they come from D2 and D0 branes. The leading term, in the regime where we trust the D-brane description, the leading term is of course the D4 brane. As you would intuitively expect, it is much heavier. So the intuitive picture is that you have a D4 brane, and then on top of it you have D2 and D0 excitations. So the ground state of your microscopic theory is like a pure D-brane, and rest are excitations.
Sorry, I missed. What is J?
J is the Kähler modulus of the Calabi-Yau threefold. It controls the size of the six-dimensional manifold, and also therefore the size of the D-branes.
Is the D-brane actually compact?
Yeah, all of them are compact. Sorry. So this D4 brane wraps a 4 cycle, D2 brane will wrap a 2 cycle, and D0 brane is just point like that. Yeah. So the excitation levels in the microscopic theory, they simply you take the mass and you subtract the divergent part, and then you take J goes to infinity limit. That will leave a finite piece, and that will be the excitations levels of your CFT. This can be made more concrete. For example, you can actually compare the ground state energies, and then there is a perfect match.
What is R?
Oh yeah, right. Not sorry, I skipped it. So the microscopic system is an effective string that wraps a circle of radius r, the in theory circle. This being a CFT, the energies appear in units of 1 over r. Actually, it's radius or circumference. Anyway, one of those two. Okay. Now we try to go to finite J. So the obvious way to do it would be not to take the limit. Very simple thing to do. But it turns out that the corresponding expressions, just this, they exactly coincide with the energy spectrum of a solvable deformation of the CFT, which is quite popular these days. It's called TT bar deformation. So basically you take a 2D theory and you deform the Lagrangian by determinant of T. This sort of work of Download also. It turns out that you can solve the spectrum of this deformed theory exactly in terms of the energy and momenta of the CFT, the starting point. So we find that in this case that spectrum arises naturally in this black hole physics. There are some other things we'd like to check. For example, we expect the same supersymmetry to hold because the supersymmetry doesn't care about the J. There is n equals to 1 supersymmetry preserved. We can argue that is the case. Modularity is a strong constant that also works out. Most importantly, since so our proposal is that this TT bar deformed CFT constitutes microscopic description of this black hole. If I come back to the picture, in this regime where we are still close to here, but still G Newton is not negligible because J is finite. The first take, of course, would be that can it reproduce black hole entropy? That it does, because to start with, the microscopic CFT explains black hole entropy. That's why we are talking about the CFT. And since the energy levels deform adiabatically, I mean, degenerate levels continue to remain degenerate levels, and you can mark them through their charges carried, which is inside the Z. So they still have the same degeneration, same entropy. So various boxes are ticked, all these things are work out.
So T here is that energy momentum tensor?
Yeah, exactly. So we seem to have this broad picture in this particular case that you start with the CFT, if you deform it, it looks like TT bar. It's of course will not, the story will not continue till this, it will change in some way. We don't know exactly how. Yeah, there is something else to the story. Skipped. Some questions are there, of course, but should I wrap up or should I briefly go through some further? Yeah, okay. So to sum up, the broad picture seems to be the following. String theory can successfully explain a wide class of black holes. I'm not claiming it's the only theory that can. And there remain open questions about certain multi-centered black holes, which I did not have time to go into, but I have worked on. One set of open questions that particularly intrigued me are questions related to thermality. I mean, of course, the story started with black holes radiating, so it's a question of obvious interest to understand similar questions in microscopic description. It has not been explored too much. And yeah, in long term, of course, the goal would be to come up with a direct description of black hole microstates, not somewhere else, but in the black hole. Thank you.